This is lesson 3.7 on polynomial inequalities. So earlier in this section, earlier in the unit, we talked about quadratic inequalities. If you recall, what we did is we factored the quadratic, and then I tried to explain we have two options. You can either look at what the graph does to figure out where the solution is going to be, or you can look at the zeros, find out where that quadratic is 0, and then check the intervals between the zeros and the two infinite intervals at either end to see if the polynomial is, whether the quadratic is positive or negative there. Polynomials are the exact same way. What we're going to do is we're going to focus on the points where the polynomial is 0. Those are going to be our starting points. And then from there, take your pick. If you want to sketch the graph using those points, again, just a very quick sketch just to determine whether or not you are above the x-axis or below the x-axis. That's a perfectly viable way to determine where the polynomial will be positive or negative. Or you can manually check within each interval. Will I get a positive value here or will I get a negative value here? Either method works just fine. We'll take a look at a couple examples where we see both approaches in action. All right, so let's take a look at this one. Let's solve this first by looking at the graph. So if we were just to graph this polynomial, so we recognize that we have zeros at 3, -1, and -4. So if I were to sketch the graph real quick, so let's put zeros at, let's see, what do we say? We said that there's a 0 at 3, 1, 2, 3, a 0 at -1, and a 0 at -4. So over here. Okay, so if we look at the power of the whole polynomial, 1, 2, 3, 4, 5, 6. So it's an even polynomial. It's positive, so I want to keep in mind, what does the graph of y equals x squared look like? So I know that it looks like this. So it tells me from my right side, I'm going to go up, or if you prefer to do it from the left side, you're going to be going up. Either way, the end behavior is going to look exactly like this. Okay, at 3. At 3, I have an odd multiplicity, so I'm going to cross through the x-axis at that point. All right, at -1, I have an even multiplicity, so I'm going to bounce off of the x-axis. And then at -4, I have odd multiplicity, so I cross through. Okay, so I want to know, where is this polynomial positive, or where is it greater than or equal to 0? So I see that is greater than 0 just to the left here, so to the left of -4, and to the right here, to the right of 3. So I'd write my answer as, I need to look at everywhere that it is greater than 0 or equal to 0. So the first place that I see that is greater than 0 is this region right here. So that is the region -infinity up to this point. That we see is -4. Furthermore, I'm going to include this point because I want to find where is this greater than or equal to 0. So I'll use a closed bracket. Next, I have to look at where I'm greater than or equal to 0. So be careful, I'm equal to 0 right here. So I need to include that single point. That single point is -1. Now, the way we include single points is a little different. We use curly braces. If you can't write curly braces well, kind of like how I can't, that's okay. Just give some sort of indication that we got a little wiggle to it. All right, then next, keep looking. We're equal to 0 and greater than 0 here. So the last part of my answer is going to be from that 0, which we know is 3, to infinity. So there's my answer. Now, another way that you could have solved this, perfectly fine. All honesty, you're doing the exact same work. Plot a number line instead. On this number line, put all of your zeros. So I'm going to put -4, -1, and 3. So there's -4, there's -1, and there's 3. Remember how when we looked at our quadratic inequalities, we said that we can take little test points in each of these intervals. So to the right of 3, I'm going to look at 4. Between -1 and 3, I'm going to look at 0. Between -4 and -1, I don't know, maybe -2. And to the left of -4, look at -5. We don't need to know if the whole thing is going to be what the exact value is. We just need to know if it's positive or negative. So an easy way we can do that is just to make a little table. Then our table, we're going to put each of our terms. X minus 3 cubed, x plus 1 squared, and x plus 4. Let me go ahead and make another little spot over here. So we want to test these 1, 2, 3, 4 different values. X equals -5, x equals -2, x equals 0, and x equals 4. We do not test the 0 points. We already know what happens at the 0 points. The function is 0, so there's no point in testing those again. Let's see here. What else can we do to save ourselves some time? If we look at this column, whatever we get from x plus 1, we are squaring it. So we know that this column is always going to be positive. So let's just go ahead and write positive for each of our entries. Since we're squaring the number that we get back, that will always give us a positive number back. Okay, x minus 3 cubed, x plus 4 to the first. That's going to depend on what x minus 3 and x plus 4 give us. So we can't just say that's always positive or that's always negative. All right, when I put a -5 here, I don't need to worry about the exact value. I know that -5 minus 3 is going to be a negative value. A negative value cubed is still going to be negative. When I plug in x equals -5 here, I again get a negative value back. So negative times a positive times a negative, I have 2 negative values. So altogether, this is going to be positive. Similar story with -2. This is going to be negative. This is going to be positive. So altogether, it's negative. 0, this is going to be negative. This is going to be positive. So altogether, this is negative. For 4, this is positive. This is positive. So altogether, positive. So I know -5 I found in that region. My graph is always positive, or my polynomial is always positive. -2 in this region, I'm always negative. 0 in this region, I'm always negative. 4 in this region, I'm always positive. So again, for our final answer, we want our polynomial to be bigger than or equal to 0. Since equaling 0 is an option, I'm going to go ahead and put in a solid dot at each of the zeros. For greater than 0, I want to find where the polynomial is positive. So I'm going to shade this region. Don't shade this region because I know it's negative. Don't shade this region because I know it's negative. And this region because it's positive. So this tells me that my final answer is going to be all the shaded parts. So this region here, I know that that is -infinity to -5 inclusive. I have this single point here. That's a little different, a little new. Don't worry about it. Just remember to put it in the curly braces. Draw them the best you can. And then the last I have this region. So that's the region from 3 to infinity. So there we go. Either way you do it, it works exactly the same way in terms of the final answer. This, I think we see, is a little quicker. So if you prefer to do it this way, if you feel comfortable with sketching the graph of the polynomial, I'd encourage you, go ahead and do it this way. It is a little faster. If this just isn't clicking for whatever reason, though, we get a little bit better glimpse of what's going on when we take a look at this table. It's a little more work, but if we're a little paranoid that we're messing something up, this might help convince us that yes, this is correct, or no, something's not quite right here. So either way is just fine. Pick the method that's more comfortable for you and stick with it. Okay, so here's another one. Solve the inequality -x cubed times x plus 2 squared times x minus 3 to the 4th is less than 0. So once again, I'm going to run through it 2 different ways. First, let's try to sketch the graph real quick, see if we can use that to help us figure out what this looks like. So we see that we have zeros at 0. So I'll put a circle there. That's terrible. Oh well. At -2, we'll put a 0. And at +3, we'll put a 0. Counting up my exponents, 4 plus 2, so 6 plus 3 is 9. I have a negative value here. So I want to keep in mind the graph of y equals -x cubed. Negative because I have a negative coefficient here, and x cubed because when I add up the exponents, so in other words, when I take the total power of my function, I get an odd value back. Now remember, if we had an irreducible quadratic term, we have to count that double. So if this were x squared plus 3 to the fourth, we'd have to count this as 8 instead of just 4. Other than that, our irreducible quadratics, they actually don't affect our inequality all that much in the same way that they didn't really affect directly our graph in terms of where the zeros are, that is. All right, so y equals negative x cubed, that looks kind of like that. So I know that here, my graph is going to go down, and here it's going to go up. Okay, now I take a look at each zero, looking at its behavior. So at 3, I have an odd power, an even power rather. So even powers tells me I'm going to bounce off the x-axis. I go to my next 0, which is 0. It has an odd power, so I know I'm going to cross through, and then I hit my next 0 at -2, which hopefully is even, meaning bouncing. Yes, so this is correct. All right, here I want to find out where the polynomial is less than 0. So I don't want to include the zeros this time, but I want all the regions where it's below the x-axis. So right here and right here. So that's going to be described by 0 to 3, the interval 0 to 3. Again, open brackets for each of them because I don't want where the polynomial equals 0. So then union with this region here, and that's going to be 3 to infinity. There we go. There's our answer. All right, if we do it the other way, let's look at our zeros. Let's make a little table. So my zeros, we again see are at 0, -2, and 3. Oh, sorry, that's not what we want to do first, is it? We don't make the table first, we make our number line first. So on our number line, we put our zeros. So 0, 3, and -2. We now pick values within each of these regions. So to the right of 3, let's pick 4, between 0 and 3, 1, -1, -3. Again, there's nothing special about the exact values. Just make sure that they're between the intervals, or between the zeros. So I'm going to look at each of these x values, -3, -1, 1, and 4. And I'm going to plug them into each of my terms here. So negative x cubed is one term. X plus 2 squared is the next one. And x minus 3 to the fourth is the next one. So x minus 3 to the fourth. All right. So since these two terms are raised to even powers, I know that it's always going to give me a positive number back. So that will save me a little bit of time. I don't have to check each of those. Doesn't matter what I plug in, I know it's going to be positive because I raise it to an even power. Here I need to check individually. So when I plug in -3, -3 cubed, that will be a negative number, but I multiply it by -1, so altogether it will be positive. -1 cubed is negative, but I want to change the sign here, so it'll be positive. 1 cubed is positive, but I change the sign, it's negative. 4 cubed is positive, but I change the sign, so it's negative. So altogether, 3 positive, so the whole thing is positive. 3 positive, so the whole thing is positive. Both of these have exactly 1 negative, so they are both going to be negative. So in this region, my polynomial is positive. This region, it's positive. Here, it's negative. Here, it's negative. So my answer, I want to find where this is less than 0. So I'll go ahead and put an open circle around each of my zeros just to remind me that I don't actually want to include it. So what I do want to include though is where it is less than 0. So I'm going to shade this region because it's negative there. And I'm going to shade this region because it's negative. So that tells me that my final answer is, let's see here, I'm not going to include -2. I put an open circle there. The open circle there is just to remind me I don't want -2. So it's not part of my answer. 0 is not part of my answer, but it is a boundary. So I'm going to put an open bracket, 0 to 3, open bracket there, and then start right back up again at 3, go to infinity. So 2 perfectly acceptable ways to approach this problem. Once again, if you can get this down, this is certainly the quicker way to do it. though sometimes doing it this way is merited. When we run into more complicated things, if we can split the function into terms like this can help us to solve more complicated inequalities, but we are not going to need to worry about that right now. So I would encourage you to understand what we're doing here, but for all practical purposes, for the drill problems, I'd encourage you, get comfortable with this because it is quite a bit quicker, particularly since we're going to need to know how to sketch these quickly anyway.